welcome back to the Quantum Rings Quantum Summer School. Last week, we learned about our first variational quantum algorithm, which was the variational quantum eigensolver. This week, we're talking about the quantum approximate optimization algorithm, which is just a very specific case of VQE, which can be used for combinatorial problems. Let's get into it. So today, we're going to be talking about the quantum approximate optimization algorithm. So the first thing we're going to do is talk a little bit about the difference between VQE and QAOA, and also their similarities. Then we're going to talk about the types of cost functions that you can optimize and the problem types that are good for QAOA. We're also going to talk about how we generate the QAOA trial state or ansatz, and then finally we'll move to the coding notebook and we'll work through some examples. So last week we learned about the variational quantum eigensolver, VQE, and for this one we have basically feedback loop between a quantum computer and a classical computer. We provide some initial guess parameter theta. We use that theta to prepare some sort of ansatz state. Then we measure for many shots to get an expectation value of the energy, and then we use a classical optimizer to come up with a new guess for theta. And then we keep going in this loop until eventually we've converged on a minimum, which we say is a good approximation for the ground state energy. So QAOA is basically exactly the same as this, but it's just a very specific case. So our U of theta is going to be based upon a cost function Hamiltonian, HC, which is set up in a very specific way, which we'll talk about later. And then, again, the goal is just to minimize the expectation value of this cost function, or cost Hamiltonian. So when would you want to use VQE? VQE is really good if you want to find the ground state and or the ground state energy of a quantum system. So for instance, last week we talked about finding the ground state energy of a H2 molecule. So basically like those kinds of quantum chemistry applications is where VQE really shines. And then QAOA is for more combinatorial problems. So you want to use QAOA for finding approximate solutions to combinatorial problems. And by combinatorial, I mean like counting arrangements, combinations. So more of like the discrete mathematics side of things rather than VQE, which is more about like physical systems. So I told you that we need to define a special cost function Hamiltonian. And there's going to be specific examples of this in the coding notebook, but the general structure is always going to be the same. It's going to be a linear combination of Pauli Z operators. And it could be just the identity. It could be Pauli Z at one location, a Pauli Z at two locations, Pauli Z at three locations, so on. So the structure of it is going to look something like this, where we have some coefficient C naught plus times the identity, plus if there's n sites, n qubits, some coefficient Cj, and the Pauli Z, sigma z, and the jth site. And when I write down something like this is implicitly saying we have the identity, center the identity, etc. And then at the jth spot, we have a sigma z, so on. And then we can also have higher order terms. So for any k greater than j, we could have cjk, sigma j, z, sigma kz. The cost function Hamiltonian is always going to take this form. And as we'll see later, this turns out to be really convenient for combinatorial problems. So recall that we can simulate the action of our cost Hamiltonian, or any Hamiltonian, by unitary evolution. So remember our favorite equation, the Schrödinger equation, which says that IH bar ddt of psi equals h times psi. And if you solve this differential equation, you find that psi at time t is equal to e to the minus iht over h bar times psi at time 0. And this is only true for an h, which is independent of time, but this is, for our case today, we're only be considering time-independent Hamiltonians. So we can make a unitary UC for our cos function Hamiltonian with some parameter gamma, which effectively acts as like time or like an angle of rotation. And this is just going to be minus e to the minus I gamma hc. So let's consider an example. If hc was just a sum of terms of the form sigma z at the site j, then our UC would be e to the minus I gamma sum over j sigma z. And then here, since all of the terms commute, Pauli z on site j commutes with Pauli z on site k, then we can actually just rewrite this as a product of all of these things, because we can break out, for instance, if you have e to the a plus b, you can write it as e to the a times e to the b. This is only true for matrices, which remember that this here is actually a 2 to the n by 2 to the n matrix. So this is only true if the matrices commute with each other, but in this case they do. Okay, now one thing that I want to point out here is, what is this unitary operation? Think for a second what you think it is. So this is a z rotation by an angle of 2 gamma. And I would encourage you to convince yourself of this if that doesn't make sense to you. One way that you can try and convince yourself of this is plug in different values of gamma and do this matrix exponentiation and see what you get. The matrix exponentiation for sigma z, so this is like 1, 0, 0, minus 1. Since it's a diagonal matrix, then e to the sigma z is going to be, or e to the minus I gamma sigma z is going to be minus I e to the minus I gamma 0, 0, e to the I gamma. Okay. Another example we can consider is this one, which has that 2 local term. And in this case, our unitary would be very similarly this. And again, since all the terms commute, we can just write this as a product. Okay, so now let's talk about the general problem structure for QAOA. It's going to be something combinatorial, where the answer is going to be a string of zeros and ones. So usually, well, you could spin it in different ways, but the most basic one is, which of n objects should I select? So for instance, let's say you have some ice cream shops and there's n towns around you with some roads connecting them. And the question is, where should I put my ice cream shops such that every town either has an ice cream shop or is next to a town with an ice cream shop? This might be something you care about. And the solution that you're looking for is basically a string of ones and zeros, which tells you, oh, where there's a 1, you should put a store, and where there's a 0, you shouldn't. There could also be more than one optimal solution, in which case there could be some set of ideal solutions. The goal here is to find our cos Hamiltonian and then minimize it. We're going to start in the initial state, which is the equal superposition state of all bit strings of length n, the classic one, which we create by applying a Hadamard gate to every qubit. If we apply UC to this state, then we'll be in this state. And let's consider what the expectation value of our cos Hamiltonian would be in this case. Okay, one thing we can notice here is that UC is just the matrix exponentiation of HC. So these two things commute with each other. That means I can change their order and nothing happens. But UC is a unitary, so U dagger is its inverse, and this will just be the identity. So nothing has changed. We've not learned any new information. So it's not super useful. Like if we just apply this unitary, we're not changing the expectation value of HC. So now we're going to pick a new unitary, which we'll call a mixing unitary, which does not commute with our cost unitary. So what do you know of that doesn't commute with sigma z? So sigma x and sigma y both don't commute with sigma z. There's lots of other correct answers too, but these are the simplest ones. So we'll call our mixing Hamiltonian this, and it would just be a sum of all the sigma x's. And then the unitary associated with that, which we can parameterize with beta, is going to be the product of all of these things. And now, what is this unitary here? This is going to be our Rx rotation of 2 beta. So now consider the state gamma beta, which is just our equal superposition state. We apply the cost unitary and then the mixing unitary. Now our expectation value is going to be this. So a couple of things here. First of all, these two do not commute. So you cannot move this unitary over. Second of all, our cost Hamiltonian and UB also do not commute because our cost Hamiltonian is in the z basis and the mixing unitary is in the x basis. So this is definitely not going to be equal to our original expectation value. And we know that that expectation value is always going to be greater than or equal to the minimum state. So we're just going to keep adjusting gamma and beta until we find the minimized expectation value, and then we say, okay, that's the approximate lowest expectation value. So if we want to improve the approximation further, then we just need to increase the depth p. So instead of having just one gamma and one beta, we'll have a vector of gammas and a vector of betas, and then we'll apply a first layer of UC, and then UB, and then a second, etc., etc., and then finally, for depth p, gamma p, and beta b. So let's move over to the coding notebook and try this out. Okay. Run the first cell to import everything that we need. And then there's a bunch of helper functions here. This is just a dummy callback, which is needed for the quantum rings estimator. Then this returns a Pauli string with the given Paulis at the given indices. We'll use this later. So basically, it's an easy way to generate strings. So for instance, we talked about terms that were like sigma zj times sigma zk. And this is actually just a bunch of identities and then 2 z's in certain locations. So for making strings like that. Here's a function to get a graph with a given set of edges, and then also plotting the cut edges on a graph given its partition, which we'll talk about later. So we can pretty easily draw graphs here. So we just define edges. So this is going to be the vertex numbers. So here we can see there's 1, 2, 3, 4 unique vertices. We can draw a graph. This is actually just a straight line, which we can see is also defined here. We can also use that function instead. And we can also see what the vertices and edges are. So we can very quickly construct whatever graphs we want. And we'll use these for our combinatorial problems. So let's do an example cost Hamiltonian. And this is just going to be for a 1D chain of length n, like this. So the cost Hamiltonian is going to be just a ZZ between nearest neighbors. And so let's think about what this cost function represents. So Z is going to be the expectation value of sigma Z. So that can either be plus or minus 1. Those are the possible measurement outcomes of sigma Z, plus or minus 1. And that corresponds to a qubit measurement of 0 or 1. So this is a way to convert between them, is that Z equals 1 minus 2x. So when x equals 0, Z equals 1, and when x equals 1, Z equals minus 1. So we're going to define that 0 means we're not selecting a vertex, and 1 means we are selecting a vertex. So for instance, 1, 0, 1, 1 would mean we selected vertices 0, 2, and 3, but not 1. So now we can consider one term in our Hamiltonian. There's 4 possibilities. So you can see here that when the qubits are in the same state as each other, the energy is 1. And when they're in a different state from each other, the energy is minus 1. So we're penalized if 2 neighboring qubits are the same as each other. And it's energetically favorable if qubits that share an edge are different from each other. So yeah, this cost Hamiltonian's ground state should have the most instances where only one vertex is selected in any pair with an edge. So now we want to implement our unitary, which implements this cost function. And we know that we can break it down as a product. So this is just a product of controlled Z rotations of angle 2 gamma. So here we can get our cost function. We can grab the number of nodes from the graph, make our quantum circuit. And then you can either do a controlled Z, or another easy way to do this is to apply a controlled knot, then a rotation on one qubit, and then another controlled knot, which for most hardware purposes, most universal gate sets utilize a C knot rather than like a controlled rotation. So let's do a controlled X, controlled on I, targeting J, and then we're going to do a Z rotation of angle 2 gamma, and that's going to be on J. And then we're going to do another controlled X. So here's an example. We could pick, for instance, gamma equals pi over 3. Here would be our unitary. So we can see the 3 edges showing up here. So then the mixer operator is going to be from this Hamiltonian, which is just all those sigma x's. And we can do that with just x rotations. So for every node, we're just going to do an x rotation of 2 times beta. And then maybe we want this to be pi over 4. Okay. So now we're ready to actually tackle some problems. The first one that we're going to talk about is the max cut problem. So suppose you have a connected graph. So that means any 2 vertices, there's some path to get through them. There's nothing that's disconnected. And you want to partition the graph into 2 sets. So you're going to select some subset of the vertices and not select the rest. And then you cut the edges between any 2 neighbors that are in different sets. What is the partition that yields the maximum number of cut edges? So let's contextualize this because it's just a lot of words. Let's draw some graphs. So here's an example graph. I want to partition this into 2 sets such that the number of edges between them is maximized. So let's think of an example, which would be 0 and 4. So these top 2 ones, let's put them in one set, and then 1, 2, and 3 in another. The number of cuts here would be 3 because we'd cut the edge between 0 and 1, 0 and 2, and 4 and 3. This is not the maximum one. Can you think for a second and see if you can find what the maximum cut is? So the max cut is going to be 5. And you can do that by picking opposite corners of the square part. Okay, another example. We can have something like this, which is like spokes on a wheel type thing. For this one, it's best if we cut all the edges and we just isolate that middle one. Here's another more crazy one. This probably you can't see just by looking at it, but we can pretty easily compute it. And the goal of QAOA is to give us an approximation for the correct answer for this problem of max cut. Okay, so here's the graph we're gonna work with. What is the max cut partition for the following graph? What should we hope to get as a result of our algorithm? And they should be bit strings. So we can actually cut all 4 edges if we pick opposite corners to be in the same set. So if we select 0 and 2 and don't select 1 and 3, then we cut all the edges, which is the maximum. So we either want the bit string 1010 or 0101. So let's define our cost Hamiltonian. We want to penalize 2 neighboring vertices from being in the same set, but we just saw this Hamiltonian in the last section. So we're just going to use that same cost Hamiltonian again, and we already know what our unitary should be. So here we have it. And then we also need to define a function for computing the energy for a given bit string. This is how we're going to calculate the expectation value of our cost Hamiltonian. We're building all of this from scratch here, and then we'll use built-in functionality in the next section. So we're given a bit string, and we want to compute an approximation for the expectation value of h. So given a bit string, what is the cost of that? So basically we're going to loop through all of the edges in the graph. And like we saw before, if the bit strings are different from each other, that's good. That's energetically favorable. And we're going to reduce by -1. And if the 2 bit strings are the same as each other, then that's unfavorable, and we increase by 1. And that's just coming from the fact that that's coming from this little table up here somewhere. Yeah, this table. And now we can create our full QAOA circuit. So we have our quantum and classical registers. We're going to create the equal superposition state. So we're going to apply Hadamard to everything in the register. And then we want to apply our layers of U, C, and UB. So keeping in mind the order, first we should apply the cost Hamiltonian. Or the cost unitary. And we're going to do gamma I. So we're providing a list of gammas and a list of betas. And we want to do this in place. And then we want to do the same thing, but with the mixing unitary and beta. And then we're going to measure our qubits. And then we want to run this. And if we were trying to get the expectation value, then we're going to compute the expectation value. So we're going to go through all of the bit strings that we measured, consider its contribution to energy and how many times it was counted, and then divide by the total number of shots to get the average expectation value. Otherwise, we can just return the counts. So let's see. Here we can choose our gammas and betas. So let's say we're just doing one layer. We're going to prepare a QAOA state for our graph with our given gammas and betas. We're not getting the expectation value, but we do want to draw the circuit to check it out. So here's our circuit. We start off with all our nice Hadamards here. Then we have our cost unitary, and then our mixing unitary is these RXs here. Yeah, here, 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 and here. Okay. So now we want to actually optimize gamma and beta, not just guess around randomly. So we need to define a cost function that we're going to minimize. So we're given x, which is just a list of gammas and betas. So the gammas are the first half of the list and the betas are the second half of the list. And then we're going to compute the expectation value of that QAOA state for those gammas and betas and return that expectation value. We want to minimize that expectation value. So here's a little chunk of code that can do that for us. So we pick the depth of our circuit. Our initial guess angles for our gammas and betas are going to be just uniformly chosen from 0 to pi. And then we're going to minimize. We can find our minimized expectation value, the optimal angles. And then we're going to extract the optimal angles, prepare the QAOA state again with those optimal angles, and get a distribution for what we measure. So let's see. So here we can see that we measured most 0, 1, 0, 1 and 1, 0, 1, 0. So that's excellent. That's exactly what we talked about before. That was the result that we were hoping for. Now we can see if we increase the depth, so p equals 2. This gets even better, a little bit better. We can do another layer too if we want. And now it's even better. So the more layers you do, the better your approximation is going to be. So I would encourage you to try this out for other or larger graphs, and then also see if you can think of any real-world applications for finding the maximum cut of a graph. The next part that we're going to talk about is minimum vertex cover. So the goal of minimum vertex cover is to cover the entire graph with the least number of selected vertices. So for each vertex we select, we can remove the edges that are connected to it, and we're done when all the edges are gone. So let's think about what our cost Hamiltonian should be in this case. We want to penalize selecting vertices which share an edge, since we want the number of selected vertices to be minimal. So I worked through the math here. If you're curious, you can read into it in more detail. But in the end, you're going to get a term in the end here. You're going to get a term that's like sigma zi plus sigma zj plus sigma zi sigma zj. And basically that term is going to give you a 0 if both I and j are included in the graph. And it's also going to give you a 0 if only one of I and j is selected. So basically what we see here is that if neither I nor j was selected, we're penalized because that means that we missed an edge, which is really bad because we need to hit all of the edges. But if one or both of them are selected, then we just get 0. But then we ideally don't want to select both of them because that's overkill. So then we also want to penalize selecting more vertices. So that's what the second term here is in this last equation, is just if a qubit is in the 1 state and the coefficient out front is -1, then that's actually going to be +1 in energy. And if it's in the 0 state, that would be -1 in energy. So we want to select as few vertices as possible. So let's pick a graph for this. Here's an example. And let's think about what are the possible minimum vertex covers here. So we can see that if we pick 2, then we'll knock out 3 of the edges, because the edge from 2 to 3, 2 to 1, and 2 to 0. And then there's one edge left, and we can either pick 0 or 1 in order to finish that off. So our ideal solution should be 1, 0, 1, 0, or 0, 1, 1, 0. So in the last part, we built everything from scratch, but this time we're just going to take advantage of Qiskit's QAOA ansatz and the quantum rings estimator, which can compute the expectation values of an operator. So all we have to do is just define our cost Hamiltonian in the right way. So we do this by making a sparse poly operator, and we just have to collect up all the poly terms that we need. So the first for loop here, we're going to get that last term in that equation. So that's going to be, this is going to be a poly string. And then it's going to be on node I is a z. And then everywhere else that's not I is just going to be identity. So then we can do append this. Oops. And now here is also going to be a poly string. And now I'm looking at this first sum here over the edges in our graph. And we basically want to do the exact same thing here. Oh, and I forgot to say, this should be a tuple with the term and the coefficient. So the coefficient here is -1. And the coefficient here is 3/4. And we also want to do that for j. And then we also want to do that cross term for both I and j. And they're both going to be a z. Okay, so let's see what our cost looks like. So we have all these different strings and the coefficients that go with them. So you can see those are our single sigma z's, and then we have these groups. This goes with every edge in the graph. So we can build our QAOA circuit. So we pick the depth that we want. Our ansatz, we're just going to use from Qiskit QAOA ansatz, and all we need to provide is just the cost Hamiltonian and the depth. And then this is really nice because we can just take that ansatz and just assign it with a theta vector, which is gammas and betas. So we just want to minimize the energy, and each time we're going to pick a new theta vector, we're going to create that ansatz. We're going to run our estimator with the observable being that cost Hamiltonian. So we're trying to find the expectation value of that cost Hamiltonian. And then we're grabbing that expectation value, and we're just minimizing that energy. So let's run it. And let's grab the optimal gamma and beta values, plug it into our ansatz, and see what we get. Okay, so our most measured bit strings was 0, 1, 1, 0 and 1, 0, 1, 0, which is what we wanted to measure. So that's excellent. So I would encourage you to try this out for other larger graphs, and then also see if you can think of any real-world applications for finding the minimum vertex cover of a graph. So that's a wrap on variational quantum algorithms, which are really the star of the NISQ era, noisy intermediate scale quantum, which is where we're at right now. Next week, we're going to talk about error correction. So how do we take a bunch of physical qubits and turn it into one logical qubit? And then how do we couple those together to make a fault-tolerant quantum computer? I'll see you then.